Okay, my apologies. That first video was 23 minutes long. Sorry, but this would have taken a couple days to get through all this in class anyway. So, crash course. Once we have the p-value and we kind of know what it means, we have to make conclusions from that. So the final step is to draw a conclusion about the competing claims being tested. So we make a decision based on the strength of the evidence in favor of the alternative hypothesis, the strength of the evidence against the null hypothesis, as measured by the p-value. If the observed result is unlikely to occur by chance when the null hypothesis is true, which means, if it's unlikely to occur at something less than 0.5, usually, then what we're going to end up saying is we will reject the null hypothesis. It's really unlikely, assuming the null is true, so it's more likely that the null is just not true. However, if the observed result is not unlikely to occur by chance, meaning you get some large probability value, then we don't accept it. You will never say that you accept. You are just going to fail to reject the null hypothesis. You're basically saying, I don't have convincing evidence to be able to reject that null hypothesis. So, like I mentioned earlier, in a criminal trial, once the jury has weighed the evidence against the null hypothesis of innocence, they return one of two verdicts. They're guilty, there's evidence to say, yeah, reject what was assumed to be true, innocence, the null hypothesis, or not guilty. You're going to fail to reject the null hypothesis. A not guilty verdict doesn't guarantee that the defendant is innocent, just that there's not convincing evidence of the guilt. A fail to reject the null decision in a significance test doesn't guarantee that the null is true, just that your sample didn't happen to give evidence for it. So again, if your p-value is small, you end up saying that you are going to reject the null hypothesis, and you're going to conclude that there is convincing evidence for the alternative. And you're going to put it in the context of the problem, as always. If it's not small, you're going to fail to reject the null hypothesis and conclude that there is not convincing evidence for your alternative. In our free throw shooter activity, we estimated with I estimated with some, what am I trying to say, simulation that you didn't actually get to see, that the p-value was really small. Because it's so small, we should reject the player's claim that the population proportion of made free throws is 0.8. So we should have ended up saying that we have convincing evidence that the player makes fewer than 80% of his free throws in the long run. So not only did we have some evidence, the p-value shows us that that evidence is convincing that the null was wrong, that p is not 0.8. In the teen calcium study, the p-value was 0.1404, relatively large, not less than 5%. So we're going to fail to reject the null hypothesis. So we're basically saying there's not enough evidence to throw this hypothesis out. We don't have convincing evidence, is how we'd interpret that. Don't have convincing evidence that teens are getting less than 1,300 milligrams of calcium per day on average. We have some evidence, but it's not convincing enough to throw out that null hypothesis. So we like to come up with a boundary line. So not just like, oh, it's less than 5%. So the common ones are 0.01, 0.05, and 0.10, just to kind of have a line drawn. There are pros and cons for the different types, but these are called significance levels. These are significance tests that we are running through. So the significance level is where that line is drawn, the threshold for is it convincing enough. It's always denoted with the Greek symbol, that's alpha. Looks like a little Jesus fish, but it's an alpha. It's the value that we use as a boundary for deciding whether an observed result is unlikely to happen by chance alone when the null hypothesis is true. Okay, so when we use a fixed significance level alpha to draw a conclusion, there are two possibilities. The p-value is less than alpha, so we reject the null hypothesis, and we say, yeah, there's convincing evidence for the null, and we put it in the context of the problem. If the p-value is less than alpha, we can say that also say that the results are statistically significant at the alpha equaling whatever number level. However, you can also have whether it's greater than alpha. This was like at the calcium problem earlier. That's when you fail to reject the null. decided to write out the longer one, but here we are. And you say there's not convincing evidence for the alternative. And as always, we throw it in context because you don't want to lose a half point from me, and you don't want to lose even more than that from me. So we would have gone through an example like this in class where a company's developed a new deluxe AA battery that's supposed to last longer than the regular AA. However, these new batteries are more expensive to produce. The company would like to be convinced that they really do last longer. Based on years of experience, the company knows that its regular AA batteries are these. Apparently these are all AAAs, and I just missed an A. They know that its regular AAA batteries last for 30 hours of continued use on average. The company selects a simple random sample of 15 of these batteries, uses them continuously until they've been completely drained, and the average of this sample for their lifetimes is the X bar is 33.93 hours. A significance test is performed using these hypotheses. Mu is the true mean lifetime in hours, and the p-value is 0.0717. What conclusion should you make? So we need to compare this p-value to the significance level. So we're going to say, because this p-value and I'll talk next lesson how to actually calculate these. Because this p-value is larger than the significance level. So they chose alpha be 0.05. It's always chosen before they run the test, before they collect their data. So they chose to be significant at the 0.05 level, but because it's greater than, we don't have evidence. So I'm going to say we were not able to reject the null like we were trying to. We don't have evidence to support the alternative. Of course, I need to we don't have convincing evidence of this, but I need to interpret that in the context of the problem. So that the true mean lifetime of the company's deluxe AAA batteries noticed a typo. The context of this problem was it being greater than 30 hours, and that is for sure not what's written up or typed up as my alternative hypothesis. So they want it to be longer, not just different, so this is wrong. It should have been written up greater than 30. It should have been a one-tailed test, not a two-tailed test. My apologies. That will definitely matter later if you get that symbol wrong. Okay, so you need to make sure you state alpha, like if you're an actual statistician, that you state your significance level first. Otherwise, you could be pretty deceptive and choose alpha afterwards. So, like if I get this number, I'd be like, oh, I didn't actually mean 0.05. I meant 0.10. And look, I'm less than that number, and that's real shady. So those always need to be chosen in advance. Because otherwise you can manipulate your conclusion, and that's just really not appropriate. However, even if you've done that, there are still errors that could have been made. When you draw a conclusion from a significance test, we're hoping that we've made the right choice, but you're going to be wrong because you're basing it off a sample, and sampling variability is a thing. It happens. We get weird results sometimes. There are two types of mistakes that you can make. One is called a type 1 error. This is if we've made the decision to reject the null hypothesis. We're like, yeah, we've got evidence. This is essentially, what is happening here? This is essentially like a criminal trial where you say, yeah, he is not innocent anymore. We have evidence that he's guilty. But in reality, he was really innocent after all. So the data gave convincing evidence that the alternative hypothesis is true when it really wasn't. That's type 1. A type 2 error occurs when we fail to reject the null hypothesis. So we're saying we didn't have convincing evidence that this person committed arson, but in reality, they committed arson. We just didn't have the evidence for it. So in statistical terms, the data does not give convincing evidence that H sub A is true when it really was true. So here's what could possibly happen. You either make one of these two decisions every time, and no matter what, one of these hypotheses is going to be true when you do these. So if you've rejected the null when the null was true, that's what we just described as a type 1 error. But if you fail to reject the null, sorry, I can't write and talk again. If you fail to reject the null, but your alternative was actually true, so you're still sitting there saying, fail to reject the null, I don't have evidence, I still think the null is true. But if the alternative was really true, you just made the wrong choice, and that type is the type 2 error. These are really easy to get confused. Don't feel overwhelmed if you don't get it at first. However, you reject the null and you say, yeah, that initial statement of equality is not true. If you end up saying, hey, look, the alternative is true, that's the correct choice to make. If you fail to reject the null, saying, I don't have enough evidence to get rid of this, and the null is actually true, again, that's a correct decision. So if the null hypothesis is true, our conclusion is correct if we don't find convincing evidence that the alternative is true. However, you make a type 1 error if we find convincing evidence that the alternative is true. So if we've rejected and it was true. If H sub A is true, our conclusion is correct if we find convincing evidence that the alternative is true. Oh no, my program just froze. Hold on. No. Aren't you glad you get to look at all this? Sorry. Type 1 error. Our conclusion is correct if we find convincing evidence that the alternative is true, but we've made a type 2 error. It's supposed to be Roman numeral 2, sorry. If we don't find convincing evidence that it was true, but it truly was. So, if there's a potato chip producer, and its main supplier agrees that each shipment of the potatoes must meet certain quality standards. If the producer finds convincing evidence that more than 8%, which is in our alternative here, of the potatoes in the shipments have blemishes, then the truck will be sent away to get another load of potatoes from the supplier. Otherwise, the entire truckload is used for potato chips. To make the decision, a supervisor will inspect a random sample of 500 potatoes from the shipment. The producer will then perform a test at the alpha being 5% significance level, and we have these two hypotheses. The p-value here is, not the p-value, the variable p is the true proportion, the population proportion of potatoes with blemishes in a given truckload. I want to describe what a type 1 and type 2 error would be in this setting and give a consequence of each one. So, a type 1 error always exists when you reject a true null hypothesis. So this would be if the producer finds convincing evidence that it's actually greater than. So I've rejected the null, I think it's greater than. Not 88%. But I need to describe that that is the wrong choice, which is what makes this an error. So the true proportion really is 8%. So I just basically rejected the null when it was a true statement. I rejected a true null hypothesis. That's a type 1 error. If this happens in this problem, he's basically saying, yeah, I have evidence that it's more than 8%. Send this entire truckload away. But it was an acceptable truckload of potatoes. It really was only 8%. So really this would be that the chip producer sends away the truckload of acceptable potatoes, wasting time, and the supplier's out of money then. So that's what I mean, or what AP means if they start asking what's a consequence, what's something bad that could happen here. So the potato chip maker, producer, not the maker. Is that the same thing? I'm not sure if it's the same thing. Producer sends away the truckload of acceptable potatoes. They thought they weren't acceptable. They really were. And because they sent away something they didn't need to, they wasted time, and the supplier lost out on some money. So I'm just going to say they wasted time and money. But that's not the only mistake that could be made. A type 2 always stems from first failing to reject the null hypothesis. So this would be, I don't have convincing evidence for our alternative hypothesis. So I'm going to write up, this would be if the producer does not find convincing evidence. Basically, I didn't have enough evidence to reject our null, so I didn't find convincing evidence for the alternative, so that P is greater than 8%. That, I have to put in context, that more than 8%, the potatoes have blemishes. So I didn't find the evidence, but in reality, the true value, the true proportion, was the thing I didn't have evidence for. The true proportion really was more than 8%. So I didn't have evidence for it. My evidence made it seem like it's still 0.8. When in reality, it was something like maybe 10%. So it was a really bad shipment overall. So the consequence would be that more of your potato chips are made with blemished potatoes, could upset the customers, could have decreased sales. That's not how you spell consequence. Oh dear. Oh, now I can't. Sorry. Even though it's only 9:40, this is my bedtime and I'm getting sloppy. Sorry. Okay, so again, this would be that more potato chips are made from crappy potatoes. Blemished potatoes. It's a nice way to say crappy potatoes. Which may upset your customers, which may end up hurting your sales. Sometimes you'll get some problems asking for the more severe of the consequence. This particular one kind of depends on who you are. So for example, if you are the potato supplier and you just had this truckload sent away and it was a fine truckload, then type 1 hurts you more. If you are the potato chip maker, this one hurts you more because you thought the shipment was fine. You used the potatoes to make those chips, and maybe people get ticked off because you got some weird looking chips being made. So sometimes it's a little more obvious. I've seen ones talking about like parachutes failing, and there's definitely like you either live or you die. You're either too safe or you overcompensate. That matters a little more than making potato chips, but okay. So in that example, a type 1 error occurs if the true proportion of the blemished potatoes in the shipment is 0.08. We get a value of the sample proportion large enough to yield a p-value that's really unlikely. So when the null hypothesis is true, this should happen 5% of the time just by chance. Because we know sampling variability happens, we're just thinking it's not likely that it'll be that dramatically low. So, in other words, the probability that you've made a type 1 error, so the probability that you get one of those values that's that unlikely, but it actually was the right choice, that's whatever you set your level of significance at. You can decrease the probability of making a type 1 error if you're like, nope, I really don't want to make a type 1 error, by just using a smaller significance level. For instance, this potato chip producer could have used 0.01 instead, but there's a trade-off. As one increases, the other decreases, assuming you don't change like sample size and other things. So if we make it more difficult to reject the null by having a smaller alpha level, we increase the probability of not finding convincing evidence for the alternative when it's actually true. So if you are an actual researcher trying to decide things, there's a good reason it's almost always at 0.05, partially just from tradition and the guy who invented all of this, but also because if you decrease the type 1 error, you increase the probability that you just made a type 2 error. So the manager of a fast food restaurant wants to reduce the proportion of drive-through customers who have to wait longer than 2 minutes to receive their food after placing an order. Based on store records, the proportion of customers who had to wait longer than 2 minutes was 0.63. To reduce this proportion, so that's what this is, reducing this proportion, the manager assigns an additional employee to drive-through orders. During the next month, the manager collects a random sample of 250 drive-through times, finds this sample proportion as 0.576. He performs this test and he sets the significance level at 10%. P in this hypothesis test is the true proportion of drive-through customers who have to wait longer than 2 minutes to receive their food. So we are supposed to first describe a type 1 error and a type 2 error for this particular problem. So a type 1 error, again, you reject the null and it was true, meaning you found convincing evidence for the alternative. I'm just going to kind of write it up over here. So a type 1 error, I wish I was typing instead of writing. A type 1 error, the manager finds convincing evidence for the alternative. So they rejected that it was equal. They found convincing evidence that it's actually less than 63%. And of course, in context of drive-through customers, I'm going to get lazy. The rest of the context of drive-through wait times are longer than 2 minutes. And again, that's the wrong choice. So if they decide that, but the true proportion really was the one that we just rejected. So the true proportion really is 0.63. So we found evidence that it's less than 0.63. It really was 0.63. That's a type 1 error. Type 2 error is where you failed to reject the null hypothesis. You basically said, yep, we don't have convincing evidence. The null hypothesis must still be true. So the manager does not find convincing evidence. So they may have had some evidence for it. It wasn't convincing evidence that less than 63% of drive-through wait times are longer than 2 minutes. But again, that's the wrong decision. The true proportion was really less than 63. So we failed to reject the null hypothesis. So we still think it's true. Should put really in there. Really is less than. So it really is. So we're left still thinking that the null hypothesis is true. And it's not, it's actually less than. Part B is which one's more serious in this case? So we're trying to figure out which one is more dramatic. So if we think about it, the type 1 error is the manager thinks that the additional employee reduces the people who have a really long wait time when it's not really the case. Whereas type 2 is they get this extra person, they don't find evidence that it's less than that, and it really was less than that. So really in this case, I'm just gonna, this one's more serious because I don't want to write that down. So again, if I were to write this out, I would just say that the type 1 error is more serious because the manager will believe that the additional employee reduces the proportion of drive-through customers who have to wait longer than 2 minutes to receive their food when that wasn't true. Based on your answer to question 2, so knowing that type 1 is the worst of the two, do we agree with the choice of 10%? So remember, this is the probability that you make a type 1 error. So if the null hypothesis is true, we're going to get a type 1 error 10% of the time just by chance. So this worst case scenario that could possibly happen to this manager happens 10% of the time just because sampling variability happens. That's not great. So type 1 error, if it's more serious, it would be better to pick a small significance level, such as 0.05 or even 0.01 if you want to get really dramatic about it. So I'm just going to say no. The probability of a type 1 error, this always happens alpha % of the time. So in this case, 10% just by chance. Which is not good if that's the worst case scenario. So it would be better to have a small significance level. As trade-offs, remember. But if that's really the thing you'd like to avoid, have a small alpha value. So they've done this test. They got 0.0385. We are supposed to tell what this is meaning here. And I'm just interpreting the p-value. Remember, this is the probability that you get a sample like you got, or something even more dramatic, if the null hypothesis actually is true. So assuming the null. So I would write out, because I've gotten really lazy, I'm not going to write this down. Assuming that the true proportion of all drive-through customers who have to wait longer than 2 minutes to receive their food after placing an order, assuming the proportion is 0.63, there is a 0.0385 chance or probability of getting a sample proportion. What was our sample proportion? Of 0.576 or something even smaller just by chance in a random sample of 250 drive-through. So it's trying to describe how common it is to get the result that you got, the sample that you got, or something even more dramatic in this direction. So that's what I would say for interpreting my p-value. There's a lot in there. I tried to find some online practice for this so you can get some immediate feedback. I promise, will get more used to it when we start the next lesson, because then you actually have to come up with these tests and do these interpretations. But it's a lot. I'm sorry we're not in class for this, but if you're following along, good for you. Ask lots of questions, email me lots of questions, and hopefully we'll get through this. So wash your hands, stay inside, stay healthy,